79 we're still with tensor product. So let me talk about the result, which is very useful in algebra geometry. So surely you know this, but it is in the framework of tensor product. That's a good point of view, so let's talk about it here. Let's start with the first part of the exercise. I'm not going to prove this, but I will use it again as before. So let phi and psi be two linear maps. I'm going to describe the kernel of tensor product of our linear maps. Okay, so phi and psi. Are linear surjective. So by our last exercise 17.8, their tensor product is again our linear surjective map. The kernel of M tensor N over R phi tensor C M prime tensor M prime over R. We're going to describe the kernel. Sure, it's a submodule of the target of the domain. Spanned by O small m tensor N, where phi m equals 0 or psi n equals 0. That is intuitively kernel of phi tensor psi equals kernel of phi tensor n plus m tensor kernel of psi. This is intuitively, while rigorously so we are again following the lecture notes of Kees Konar on the internet. So more rigorously, we should be more careful, because as we have saw in the last exercise, so tensor product of injective linear maps is not necessarily injective. So in terms of the inclusion maps, so we know I is injective, J is injective, but this doesn't tell you necessarily I tensor identity and J tensor identity is injective, and the kernel should be rigorously described as I tensor 1 over kernel phi tensor N plus 1 tensor J tensor with kernel of psi. The reason kernel of phi tensor n plus m tensor kernel of C is intuitive. Is that these tensor product modules are not necessarily submodules of M tensor and R. Which means this. You cannot say why they are submodules. Only after applying one tensor one, for example, so this is from kernel phi tensor n to m tensor n, and so you know the image is a submodule. To them, do those modules become submodules? And even though this might not be injective, okay, so this is our slogan last video. Tensor product of submodules might not be a submodule. Okay, so I'm not going to prove this, but I'm going to use this second part. Think of this as corollary. Let F be a ring homomorphism of commutative rings, and let I be an ideal in this polynomial ring. And we write I polynomial ring S x1 xn for the ideal generated by the image of I in this ring. And then what is asked to prove is that as tensor over R with this polynomial ring, several variable quotient I with isomorphic to first base change ring, and then quotient is ideal of this base change ring as S modules by the map small s tensor small h mapped small s times small h bar. Okay, so let's prove this. So actually, yeah, as I said, this is basically is telling you how is a fine variety look like after base change. What is the coordinate ring after the base change, right? So proof. The identity map from the ring S to S, in particular as R linear map, and the reduction map, in particular are linear, are both surjective maps, right? And so by our exercise in the last video, the tensor product of the two maps is again surjective. Let's denote by S tensor over R with polynomial ring, and then surjective onto S tensor over R with quotient ring, right? So we just have to describe the kernel. So by the exercise 1 of today's exercise, the kernel is one tensor J over S tensor I. So notice for this one, its kernel is I, right? Let's call this phi, this C. So the kernel is, recall is intuitively it's kernel V tensor with 1 plus, sorry, kernel V tensor with whole ring plus whole ring tensor with kernel of C. Intuitively it's like this, right? And the kernel of V, this is 0. So we don't have this term. Kernel of C is I R X I, right? So as we said, put it more rigorously, you should write in this way. Is the image of S tensor with kernel of G or kernel of C, where J is the inclusion map from the kernel more rigorously, it's this from the kernel. To the ring, the inclusion map. Okay, and recall. So recall. This is basically one tensor J over all the elements of it, right? Let's call it alpha. And this is just the elementary tensor, and then you could take all the summation. And we just have to describe this submodule and the submodule of this, of course. But also recall we have here, this is the same as polynomial ring. You could this is very quickly, this is very easy to just prove it directly. You just show this is a bilinear map and then surjective and injective. Okay, this is very easy to prove. And so notice one tensor J over S tensor R as a submodule of here. So let me record one more time. So you have S to S identity, you have J, the inclusion, which gives you this map. Right. So what is the image? We want to describe the image. Right. So let's just quickly recall. So this is just, this map is just so let's just describe the elementary tensor. So just very quickly, so this f x I, this is mapped just as I f x I, so the coefficient is as I, and so for similar reason we do this. This is just an element here, which if you want you could write it as I times f with I element in I. It's, let's say, alpha f, and then this is mapped S alpha f, and so alpha alpha is in I. I is the ideal of R xi. And so the kernel finally is I times S xi. And so finally we are down, so the kernel is described. And so finally it's S quotient by I, S is isomorphic to S tensor. R quotient I.